Hello class, in this video we will speak about projectile motion, so let's get started. When the player kicks the ball moves in a curved path. This is an example of a projectile. In order to study the projectile, let's consider the following steps. We start drawing the XY system by locating the position of the origin O. We choose the origin O to be the launching point of the projectile at t equals to 0. Let's draw our system here. At t equals 0, the ball was given an initial velocity v0 that makes an angle alpha with the horizontal. Then we draw the x-axis. We choose the x-axis to be horizontal, and we choose the positive x-axis to have the same direction as v0x. In this case, it's to the right. Then we draw the y-axis to be vertical, and we choose the positive y-axis to have the same direction as v0y. In this case, it's upwards. Then on the x-axis, we draw the unit vector I, where I is directed in the same direction as the positive x-axis and has a magnitude of 1 unit. Similarly, we draw j, the unit vector on the y-axis, such that j is directed upwards as the positive y-axis. Now let's draw our system here. We are ready to move to step 2. By the initial conditions, we mean the values of r0 and v0 at t equals 0. So at t equals 0, the ball was at the origin. So x0 equals 0 and y0 equals 0. So the position vector also equals 0. What about the velocity vector v0? v0, and as any vector, can be dissolved into two components, v0x and v0y, where v0x is the projection of v0 on the x-axis, and v0y is the projection of v0 on the y-axis. So we can write v0 as v0x in this direction plus v0y in this direction. Usually you're not given the values of v0x and v0y. Instead, you're given the values of v0 and alpha. So let's find v0x and v0y in terms of alpha and v0. If we look at this triangle here, sine alpha equals the opposite over the hypotenuse. So it's equal v0y over the hypotenuse, which is v0. So v0y can be written as v0 sine alpha. What about cosine alpha? Cosine alpha equals the adjacent over the hypotenuse. So it's equal v0x over v0. v0x can now be expressed as v0 cosine alpha. Let's insert the values of v0x and v0y in this equation. After finding the initial conditions, we can move to step 3. Newton's second law states that the sum of forces acting on an object equals its mass times its acceleration. The only force acting on a projectile while in motion and after neglecting all the air resistance and frictional forces is the weight of the projectile directed vertically downwards. So W or mg equals ma. Cancelling m from both sides of the equation, we get g equals to a. What does this equation tell us? When we have two vectors that are equal, it means that they have the same magnitude and the same direction. The magnitude of the acceleration then equals the magnitude of g, which is about 10 meters per second square, or as indicated depending on the location of the projectile. And the direction of A is the same as the direction of G, which is vertically downwards. We still have to express the acceleration vector A in terms of the xy system that we have. Since A is vertically downwards, it means that it doesn't have a horizontal component. It only has a vertical component. So the magnitude of A is G, and it has a vertical component only, so it is on this line. Now, since A and J have opposite directions, because J is directed vertically upwards and the acceleration is directed vertically downwards, then we add a minus sign here to indicate that these two vectors, I mean A and J, have opposite directions. After indicating the acceleration vector, we can move to the last step. In the last step, we want to find the values of the velocity vector and the position vector of the projectile at any instant. So how do we proceed? We start from this equation here. So A equals minus Gj. And as we said, that this factor here is constant, and this is a y, and it is constant. We want to find the value of the velocity vector, which is the antiderivative or the integral of the acceleration vector. So v equals, and the antiderivative of a constant is the constant multiplied by time. So this is minus gt, j. Plus we have to add the constant. And the constant, we can find it from the initial conditions. So the constant is v0. Why is the constant v0? Because the value of the velocity at t equals to 0, when we remove this factor, is equal v0. So when we remove the factor which contains time, then the value of the velocity equals v0. And v0 we can find it from the initial conditions. Rearranging the equation, we get we can notice that the velocity vector, and unlike the acceleration vector, has two components. So here we have Vx, and here we have Vy. We can also notice that Vx doesn't depend on time. So this is a constant. V0 is constant and cosine alpha is constant. So this Vx doesn't depend on time. And it makes sense because there is no net force acting on the projectile on the horizontal axis. The only force acting on the projectile is the weight, which is on the vertical axis. Now in Vy we have two components. One of them is constant and the other one depends on time. Now we want to find the position vector, which is the antiderivative or the integral of the velocity vector. So this is a constant, so r equals v0 cosine alpha times t. This is also a constant. Okay, this is gt, and the antiderivative of a constant times time is gt squared over 2. And all of these multiplied by j. We also have to add the constant, which is r0. Again, why do we add r0? Because the value of r at t equals to 0 is when we remove all these factors that contain the time. So r equals r0 at t equals 0. But from where do we get r0? We get it from the initial conditions. In this case, because the ball started from the origin, r0 equals 0. So we can remove this factor. This is everything for this video.